Okay, welcome everyone to the 147th meeting of New Directions in Group Theory and Tangled Categories. Our speaker today is Ishan Levy from IAS Princeton, and he will be talking to us about telescopic stable motion theory.
Thanks so much. Yeah. So I'm going to tell you, this is going to be like an overview talk. So I'm really just going to give an overview of some recent developments, and some of what I'm saying is not written yet. So my apologies for that. Uh, so yeah, I want to tell you about telescopic stable homotopy theory, and to motivate it, maybe if you're interested in, well, it's the triangulated categories or stable infinity categories, then you should be interested in we're interested in spectra. Uh, for example, it's freely generated as a stable infinity category by a single object. So it's kind of a universal example. It's also the initial symmetric monoidal stable infinity category. Uh, Maybe with presentable stable infinity category. And let's just recall that it has a unit, which is the sphere spectrum, which I'll denote that like this. And it has the property that if you look at homotopy classes of maps from the ith suspension of that to itself, that is the stable homotopy groups of spheres, namely pi n plus I of Sn, where n is at least maybe I plus 1. It's larger than I plus 1. And just to simplify things, I'm going to fix a prime p, and I'm going to work p locally. So, um, so it's the initial p local symmetric monoidal presentable stable infinity category, and I'm going to denote the p local sphere just as the sphere. And now these are the p local stable homotopy groups of spheres. Okay, and so the sort of the the biggest question is sort of what are these stable homotopy groups of spheres? That's sort of a proxy at the question, how does stable homotopy theory work, or how do these stable infinity categories work? It's one way to try to understand that question. And there's an approach, which is sort of the telescopic approach to understanding this question. And it goes as follows. So the question is, what is pi star of S? And what you can do is you can start with the sphere, and you can map to the sphere where you inverted P. And by this, I just mean the filtered colimit of multiplication by P as a self-map of, which is sometimes called a telescope of multiplication by P. And it turns out that this is just the spectrum that is the rational numbers. In other words, it has its homotopy groups are Q in degree 0 and 0 otherwise. And this is so we know the pi star of this of the sphere after inverting P, and this is essentially due to Serre. Okay, so you can think of this is some part of the stable homotopy groups of spheres that we understand. We understand what happens after you invert P. But then you can say, what did I miss by doing that? And well, essentially what you missed was whatever the homotopy groups of the cofiber of this map is. And the cofiber of this map from the sphere to the rational numbers is the colimit over n of the sphere mod p to the n. And so, and here by the sphere mod p to the n, what I mean is just the cofiber of the p to the n self-map of the sphere. And so what you can interpret this result as saying is that you've reduced the study of the stable homotopy groups of spheres to the study of the stable homotopy groups of spheres mod a power of prime b of a prime p. Okay, so what do we know about that? Well, it turns out we can do something similar. Namely, we can take sphere mod p to the n, and we can there's a self map which is not it has some degree now, called v1, and you can invert some power of that v1. So you can take the sphere mod p to the n, you can invert v1, and so here v1 is maybe it's really v1 to some power. This is some map from some suspension of the sphere mod p to the n to itself. So some map that exists. I mean, these are sort of constructed by atoms in the 60s, these kinds of maps. And you can invert that map, which is some kind of telescope, some co-limit like this. And again, this is a situation where we completely know the homotopy groups. So we know pi star of this. For the prime 2, this is due to Mark-Mohoald. And at odd primes, this is due to Haynes-Miller. This is maybe in the 80s. And so again, this is some part of the homotopy groups of this object that we now understand. And you can ask, what did we miss by understanding, by what did we miss from just this? And what we missed was the co-limit. We sort of missed the homotopy groups of objects that look like the sphere mod some power of p and some power of v1. So namely, it's something like the co-limit of, maybe you have this negative suspend by the degree of v1 to the m1. Okay, but the point is just that you can interpret this result as saying that now you've reduced the homotopy groups of understanding the homotopy groups of spheres to understanding the stable the homotopy groups of this object, of these objects. Okay, so we've reduced the problem to pi star of these kinds of things. So sphere mod some power of p and some power of v1. Okay. And you can keep going. So namely, I'll just tell you what we know about how this process keeps going. So this really comes from the work of Devenants, Hopkins, and Smith. So what Devenants, Hopkins, and Smith showed, they showed that there are a sequence, you can keep going and you can build objects that look like the sphere modulo some power of p, some power of v1, all the way up to some power of vn minus 1 to the mn minus 1. So you can keep modding up by some sequence of elements, and this is called the type n complex. It's an example of a type n complex. And these objects, they have what are called Vn self-maps, which you can sort of heuristically think of them as a power of Vn, which it's a bit of abusive notation because Vn itself might not be a self-map, but some power of Vn will be a self-map. So these have some sequence of self-maps. And so you can similarly keep reducing the problem of the stable homotopy groups of spheres essentially to understanding. So you can reduce. So let me give a name to this. So I'll call this I'll just call this V sub n. Okay, and you can reduce understanding pi star the sphere, to pi star of these Vn's after inverting this self map. And this is the telescope. It's called a telescope of inverting the self map. So it's a telescope of a type n complex. Right. And so Yeah, so this method keeps going. And moreover, it's kind of the only thing that you can do in the following sense. So if you think about inverting an element uh, in a commutative ring, it doesn't really, it only depends on that element up to nilpotence. Like if you change the element you're inverting by a nilpotent element, it's not really going to change what you get. And so you can ask, like, why did I invert V1? Why didn't I invert some other element? And the reason is because, for example, well, so what Devon, Hopkins, and Smith prove is that if you take the homotopy ring of the sphere modulo, if you take the homotopy ring of the sphere modulo p some power of p all the way up to some power of vn minus 1, so this vn, and you mod out by nilpotence, then this is actually a subring of a polynomial ring on this Vn. And maybe I'll just tell you the degree of Vn. So Vn is it's a self map of degree 2p to the n minus 2. Okay. So right. So what this is essentially saying is that you only have one option if you want to keep breaking up the stable homotopy groups of spheres into by inverting or modding up by an element. The only options you really have are to mod up and invert these VNs, and you sort of reduce the problem to understanding the homotopy groups of these telescopes. These are called telescopes. Okay. And I sort of mentioned over here that we know the homotopy groups in the case of the 0th telescope and the first telescope. But actually, we don't know this. We don't know what the homotopy groups are ever for n larger than 1. So for n at least 2, we don't know this. And so so the telescope conjecture is sort of it's a conjecture that was made by Doug Ravenel to try to understand. Well, I mean, one way to interpret it is it's sort of a prediction as to what these homotopy groups should look like. And here's one way to think about it. So first, let's think about what happens when n equals 1. So for n equals 1, what's the reason that we can understand the sphere? So V1. So V1 is just maybe the sphere mod p to the n. And the reason we can understand the homotopy groups of the sphere mod p to the n after inverting V1 is because of an isomorphism of spectra. So there's a map from this to the following thing. You can take you can take the complex K theory spectrum, Ku, and you can mod that out by Vn, by p to the n. And that has a map from the sphere because it's the unit map, essentially. And the Ku mod p to the n has an action of Adams operations. So there's this action of this group ZP cross, the p-adic units on this, and you can take the fixed points of that action. And the theorem is that this is an isomorphism. And so the point is that you know the homotopy groups of this. And this isomorphism is exactly how Mahold and Miller, well, it's one way, I guess, you can compute the homotopy groups of this is by knowing this isomorphism and then seeing that we know how to compute the homotopy groups of this. So the telescope conjecture is the hope that something like this is similar, something similar to this holds for larger n for larger n's. So namely, so you replace Ku with a certain commutative ring spectrum called Morava E theory, and you replace this action of the CP cross with an action So I guess Ku after p-adic completion has this action of ZP cross coming from Adams operations. And Morava E theory has an action of what's called the extended Morava stabilizer group, which is some group that we understand. And the point again is that we know the homotopy groups of this. We know pi star of this. It's just it doesn't really matter what the explicit formula is, but I mean for the purposes of this talk, but it's the Witt vectors of the algebraic closure of FP, and then you take some power series ring on several generators, and then you add a periodicity class in degree 2. So it's just some explicit ring that we know. And the conjecture, so the telescope conjecture of Ravenel is the conjecture that when you take this Vn and you invert this, you take the telescope of this type N complex, that's the same as what you would get by doing the same thing, but then tensoring with this Morava E theory, and then taking the fixed points by this group action. And the point is, this is what one way to think about this is that it's saying that well, it's saying that the homology of this telescope with respect to this spectrum doesn't it sees everything. So the point is that we can often compute the homotopy groups of this. Can compute pi star in principle. And so the point is that this is sort of giving a description of the spectrum, in particular homotopy groups, in terms of something that we understand much better. Okay. Let me know if there are any questions. So, I mean, yeah, I guess if you're familiar, well, okay, I will mention this later, maybe. So, right, so this conjecture, it's true for n equals 1. This is essentially the result of Mahold and Miller, and it's false for n at least 2, and this is the result of Robert Burklund, Jeremy Hahn, myself, and Tomer Schlank. Right. Okay, so I want to explain sort of a categorical formulation of this conjecture. So I guess the way I've motivated the conjecture is in terms of something about certain parts of the homotopy groups of spheres, but there's sort of a way to think about it categorically. As follows. So you can start with the category of spectra, and there's this symmetric monoidal localization of it called the Tn local category. And the localization I'll denote as sub Tn. And this localization has a right adjoint. And what is this localization? It's the presentable localization. It's a colimit preserving localization such that a map becomes an equivalence after you localize if and only if it's an equivalence after you tensor with the telescope of a type N complex. Okay, and so you can think of this as the part of the stable homotopy category that that these telescopes are sort of aware of. I mean, if you're familiar with this is sort of an aside note. If you're familiar with Balmer spectrum, there's maybe a more familiar way to say what's happening here, which is that the results of Devenatz, Hopkins, and Smith tell you that the Balmer spectrum of this category of p-local spectra is it's the following space. It's the space which has points labeled by the natural numbers in infinity, and this is sort of the universal support of finite spectra, and the support of Vn is exactly the subset of things n and beyond. That's some closed subset of this topological space, and this localization is exactly the localization that corresponds to the locally closed subset of just the point n. Okay, so this is I mean, yeah, if you don't know what that means, it's not relevant. This is one way to think about what this localization is. So it's it sort of naturally comes from thinking about the geometry of the category of spectra. And so right. And so the point is that there's this one way to reformulate the telescope conjecture is it's sort of about whether this is the same as a further localization. So there's a further presentable symmetric nodal localization called KN localization. And what that is, well, here's sort of an easy way around defining it. So it's the presentable localization such that a map Kn locally is an isomorphism if and only if when you tensor with the telescope of a type n complex and you also tensor with this fixed points of this Morava E theory, then you get an isomorphism. So you can see that that's very related to what the telescope conjecture was the two sides of the telescope conjecture. And so the point is that the telescope conjecture, oops, so something's wrong with my pen. Yeah, so the telescope conjecture is for n, for this n, for height n, is equivalent to the statement that these two categories are the same. So it's equivalent to the question of is this an equivalence of categories? Maybe another. So you might think, why would you consider like what's so special about the Kn local category other than the fact that we can understand we can understand homotopy groups inside of it. It is actually kind of not it's a reasonable thing from a categorical point of view. One way to say it is this localization from the Tn local category to the Kn local category. It's the terminal non-trivial strongly continuous localization. And so I'll say what that means. So in other words, it's the functor that is colimit preserving. It's a functor that's colimit preserving. It's strongly continuous, which means that it preserves compact objects. So both of these categories are compactly generated. And it's non-zero. Yeah, so it's sort of the terminal object. The terminal looks such localization. Okay, so that's the categorical formulation of the telescope conjecture. I want to tell you a bit about the mechanism of how it fails. So, so the mechanism of the failure is through something called cyclotomic descent. So, or yeah. So, namely, so there are certain. So the Tn local sphere, the Tn localization of the sphere spectrum, that's a commutative algebra in the category of Tn local spectra. And there's what's called a Galois extension in the sense of Rogness of this commutative. This is like a commutative ring in T and local spectra, and it has a Galois extension, which are called the chromatic cyclotomic extensions. So these are Z mod P to the K cross Galois extensions in the T and local category. So these are constructed by Carmeli, Schlank, and Yanovski. And they're Galois extensions, so they have an action of the Galois group, which is the units inside Z mod P to the K. And they're called cyclotomic extensions because they really do generalize the usual cyclotomic extensions. Namely, if n equals 0, then the Tn local sphere is just the rational numbers, and this extension is just adjoining a primitive p to the k root of unity. Okay, so the point of the failure of the telescope conjecture, or the mechanism for it, is that for at least 2, what you can do is you can look at the infinite cyclotomic extension. Namely, you can take the co-limit of all of these finite extensions. So I'm just going to denote that by omega p infinity. And then you can take this co-limit and, or actually, it doesn't really matter. Maybe I'll just write co-limit over k of all of these extensions, and then you can take the fixed points of that by the inverse limit of all the Galois groups. So that's a ZP cross. And we can just give this spectrum a name. So we can call it the cyclotomic completion of the Tn local sphere. And it turns out that modules over this algebra in the Tn local category, they form again a strongly continuous localization. Namely, if you start with Tn local spectra, you can tensor with this object, and that gives you, tensoring with that object gives you a symmetric monoidal localization onto a subcategory that you might call the cyclotomically complete category. And so because the Kn local category is the terminal, strongly continuous localization, this factors the map to the Kn local category. And so you have this factorization of Kn localization through this other category. And we in fact show that this is not an isomorphism for n at least 2. So this is the mechanism of the failure of the telescope conjecture. And maybe I'll mention that we in fact don't know in general, is this map an isomorphism? And it seems to be true at some small heights, but we're not sure in general. But it seems plausible. Okay, so that's the mechanism for the failure of the telescope conjecture. Let me tell you a bit about how we prove it. So the disproof of the telescope conjecture uses algebraic K-theory. So namely, we construct a certain ring spectrum, so a certain associative algebra inside spectra called BP. These are sort of known to exist. So they're pretty nice ring spectra. So for example, we completely understand their homotopy groups. Their homotopy groups are just a polynomial ring from V1 to Vn over the P local integers. And what we construct is we construct certain automorphisms of this ring, which we call Adams operations. And I mean, the reason that's a reasonable name is because when n equals 1, then BP1, it's actually the Adams summand of Ku, of the connective K-theory, complex K-theory spectrum. P localized, and the automorphism is the atoms operation. So the action is the atoms operation. Okay. So we construct these rings, and then the point is that we use algebraic K-theory of these rings, or maybe the fixed points of these rings, to provide counterexamples to the telescope conjecture. Namely, so let me just set that up. So there's this functor algebraic K-theory, which is it takes in an algebra in spectra and outputs a spectrum. So this is algebraic K-theory. And we show, and at least one, that if you take the Tn local, so I'm going to denote the Tn plus 1 localization of K-theory by K sub Tn plus 1. So the Tn plus 1 local K-theory of this BPN, if you take the fixed points of that by any non-trivial subgroup of the integers, so namely, like you could take the fixed points by p to the kz, and then maybe you also want to Tn localize this. That's not so important. So we show that that is not isomorphic to what you get when you cyclotomically complete it. So if you cyclotomically complete it, and so that shows that these two categories aren't the same, because this is an object that's in this category, but it isn't, it changes after you localize it into this category. Okay, and so how do we show something like this? Well, I'll just tell you the key ingredients. So, so the first ingredient is this result of Ben Maché and Carmeli, Schlank, and Yanovski. And what they show is that this map agrees with the following map. So agrees with maybe I'll just say these maps agree. So instead of looking at the cyclotomic completion map, you can just look at the following map. So take the Tn plus 1 local K theory of this ring, and then you can look at the co-assembly map. So in other words, the map measuring whether or not this functor commutes with this fixed points. So you can map this to the Tn plus 1 local K theory of this ring, but then you take the fixed points after taking K theory. And the first result, which is called cyclotomic redshift, shows that these two maps agree. And the key ingredient here is that K theory really interacts well with cyclotomic extensions. So this functor sort of sends cyclotomic extensions to cyclotomic extensions. That's what they show. And so if you want to show that this isn't an isomorphism, you just need to show that this isn't an isomorphism. Okay. So that's the first step. The next step is to replace K theory with a functor that's more tractable, namely topological cyclic homology. And so there's this natural transformation from K theory to this functor, topological cyclic homology. And the point is just that topological cyclic homology is much more tractable to compute and to work with sometimes. It's topological cyclic homology. Again, for the purposes of this talk, it's not really important that you know what this is. So the key point is that this K theory that you're interested in a bunch of results, so sort of some recent and some less recent, identify the K theory. Well, okay, yeah, they identify this Tn plus one localized K theory with Tn plus one localized Tc. So namely, this is just the same as the Tn plus one localized Tc of Bpn, and then you take the fixed points by e to the kz. And so this is really due to a lot of people. Dundas, Goodley, McCarthy, I'll mention, Clausen, Matthew, Naumann, and Noel, and Land, Matthew, Meyer, and Tama. And on this side, something similar is true, but these results don't quite suffice. You need to, in addition, have a result of myself that tells you that these comparison theorems about K-theory and TC also hold for rings like the fixed points of VPN by these Adams operations. And so what you end up with is that you can replace K-theory with TC in this comparison map, and you can remove this Tn localization on the VPN. So namely, it's enough to just study this map. So it's enough to show this is not an isomorphism. Okay. And moreover, it's actually not so hard to see using the fact that cyclotomic completion is a smashing localization, that it's actually enough to show that this is not an isomorphism for k sufficiently large. You don't need to show it for small k. Like if you showed for a larger k, it'll automatically imply it for a smaller k. Okay. So how do you show that? Well, the key point is that so to show that some map Tn plus one locally is not an isomorphism, by definition of the Tn plus one localization, it's enough to show that the map after tensoring with a telescope is not an isomorphism. So it's enough to show that this map after you tensor with a telescope is not an isomorphism. So it's enough to show that this map is not an isomorphism. And for example, it's enough to show that the level of homotopy groups. And so what you can do, so one of the key technical points in the paper is that we actually show that when k is sufficiently large, so sort of for k sufficiently large, we show the following square. We show that there's a square of isomorphisms. So you can replace again this map, this comparison map, with the same comparison map that you would have gotten if you replace this Adams operations with the trivial action. So namely, you're allowed to replace this Adams operations over here, which is a non-trivial action, with the trivial action, as long as k is sufficiently large. This is one of the key technical points. And so once you show this, it turns out that so by bp to the kz, I just mean this is like the fixed points by a trivial action. This is the fixed points by the trivial action. So basically, you're just allowed to replace the action with trivial action. And now the point is that this map, this is not an isomorphism for very general reasons. For very general reasons, namely, it follows from the fact that it follows from the fact that just Tc of this BPN, Tn plus 1 locally, is non-zero. And this fact is due to Ausonian Rogness for maybe for n equals 1 and p at least 5, and it's due to Hahn and Wilson in general. Okay, and so yeah, so this is how we essentially show that this is not an isomorphism. So it comes down to some facts about topological cyclic homology. Okay, so I want to tell you some consequences of this. So, the telescope conjecture was making a prediction about the stable homotopy groups of spheres. So what can we say now about the stable homotopy groups of spheres? Well, one thing we can say is that they're very big. So I want to explain how, like why this sort of tells us a lot about the size of the stable homotopy groups of spheres. So there's a construction you can do as follows. So if you can start with the Tn local sphere, and you can look at the unit map into this Galois extension, this cyclotomic extension. And the cyclotomic extension has an action of ZP cross. So just choose some element, maybe a generator of ZP cross, of Z mod P to the K cross. Let's call it sigma. And you can look at 1 minus the action of sigma. And that map, so this composite is null because of the fact that this is the fixed points of that. And therefore, if you, 1 and sigma are the same after you precompose with the unit. And so you have a null homotopy of this map. And you can dualize this whole picture. So the dual of the unit map is a trace map from this back to the Tn local sphere. And the dual of the fact that you have a null homotopy here is the fact that this composite is also null. And so the fact that now you have 2 null homotopies from the Tn local sphere to itself of this whole composite gives you an element of pi1 of the maps from the Tn local sphere to itself. So namely, this construction gives rise to an element called tau k in pi1 of the Tn local sphere. So this is some family of elements inside the Tn local sphere. And so with Robert Burklund, Shachar Carmeli, Jeremy Hahn, Thomas Schlank, and Leo Yanovski, we show that these tau k's, they're actually linearly independent, even mod p, for k sufficiently large. So the homotopy groups so this pi1 is really quite large. It's sort of infinite, it's infinite rank. For n at least 2. This is when the telescope conjecture fails. And in fact, we show not only are they independent here, they're even linearly independent in pi1 of so you can look at the image of pi1 of this sphere mapping into pi1 of this topological cyclic homology of one of these BPNs, fixed points, like the object that was essentially the counterexample of the telescope conjecture. You can just look at the image in there, and it's still non-trivial. They're still linearly independent here. And so what you can learn from this, like a consequence of this, is that pi1 of this telescope for n at least 2 is infinitely generated. And so if you think about what that's saying that pi1 of this type n complex, the ranks of that grow larger and larger as the degree gets larger and as you multiply by Vn. And so for n equals 2, you can actually be more precise. So for n equals 2, you can sort of bound how many multiplications by V2 are needed in order to construct tau k. How many V2s are needed to construct tau k. And so you can, what you learn is you learn an explicit lower bound on the size of pi1 of this type n complex. And since the type n1 complex is just built out of finitely many spheres, except finitely many copies of the sphere, you also learn a lower bound on the size of the homotopy groups of spheres. And so I'll just tell you sort of a sort of concrete way to formulate that. So one way to formulate that is you can take the average. So this is the average from 0 to n of the rank over fp of the homotopy groups of spheres mod p. So this is an fp vector space. And what you can show is that this asymptotically grows large at least like log of n times a constant. So this is sort of a consequence of this. And it turns out that the same thing is true unstably. So with Arone, we use sort of some unstable homotopy theory, namely things about the Goodwillie tower and how that interacts with these telescopes. You also get a similar lower bound unstably. So you get a lower bound unstably as well. And these are really the best lower bounds that we have on the growth rate of these of the stable homotopy groups of spheres. So this is the best way we know to construct elements of the stable homotopy groups of spheres. Okay, so that's something about consequences. I want to now say a little bit about something about like something conceptual about the difference between the Tn and Kn local categories. So the Kn local category is one that we understand quite well. And so, for example, we understand exactly what the Galois extensions of the Kn local sphere look like. So namely, it turns out that this Morava E theory is kind of it's like the separable closure of the Kn local sphere. Namely, it's the co-limit of all the connected Galois extensions of the Kn local sphere. So if you recall, so what's true is that if you take this Morava E theory, it has this action of this extended Morava stabilizer group. And the fixed points of Morava E theory by this extended Morava stabilizer group is exactly the Kn local sphere. And this En is actually a filtered co-limit of finite Galois extensions. So namely, there's a sequence R1, R2, and so on of finite Galois extensions. So these are finite Galois extensions, and the co-limit in the Kn local category of these Ri's is En, and the inverse limit of their Galois groups, which are finite, is exactly this Morava stabilizer group. And so in this Kn local category, you have the Galois theory. It just works perfectly in the sense that the Kn local category is just equivariant Kn local modules over this this Morava E theory. And so yeah, so Galois theory just works perfectly well, Kn locally. And the theorem I want to mention with Robert Burklund, Dustin Clausen, is that this is sort of this phenomenon about Galois, infinite Galois descent is sort of exactly the difference between the Tn and Kn local categories. So more precisely, what we show is that similarly to how we have this tower Kn locally, there exists a lift of this tower. There exists a lift of this tower to Galois extensions. So you start with the Tn local sphere, and there's some R1 tilde, which is a finite Galois extension with the same Galois group. Some R2 tilde, again a Galois extension with the same Galois group, and so on. And the co-limit of all the Galois extensions of the Tn local sphere we show is, in fact, again, Morava E theory with its action of the Morava stabilizer group. And so what this is saying is that the difference between the Kn and Tn local category is that in the Tn local category, you only have Galois descent in general for the finite Galois extensions of the Tn local sphere. And if you go to the infinite Galois extensions, you might get something Kn local instead. So, failure of the telescope conjecture, it comes exactly from the failure of infinite Galois descent. And so something that remains a bit unclear is, does the failure come from smaller extensions, yeah. So what do I mean by that? So for example, you could imagine that you don't need to look at this tower. In fact, it's just enough to look at the cyclotomic extensions. So for example, is the cyclotomic completion, which is this already? So in other words, if you take the Tn local sphere and you adjoin all these roots of unity to it, is this Kn local already? Yeah, so I don't have much more to say. Maybe I'll just mention what I think is the biggest open question, or maybe it's not the most. It might not be the most interesting question, but it's a proxy to what we're interested in the sense that if you can answer this question, I think that will mean that you'll have understood the Tn local category very well. So the question is, how do you compute? Can you compute? Can you compute pi star of a telescope? So the telescope conjecture was sort of a prediction as to what this should be in terms of the answer Kn locally. But we still don't really have any methods for trying to attack this at the moment. Like what we now have is we have these TC spectra, which you can use to detect. You can use them to detect information. So there's a map from here into these TC spectra, and we can use it to detect information, but we don't really have a way of just computing the whole answer, which we often can do in stable homotopy theory. So I think if you can understand this, then that will be a sign that you really are starting to get strong control in the same sense that we have over in the Kn local category in the Tn local world. So I'll stop there.
Thank you, Ishan. Let's all give the speaker a round of applause. Right, so if you have any questions, please ask them.
I have a question. Who are the co-authors in that last theorem?
This theorem.
Yeah.
This is Robert Burklund,
Yes.
and this is Dustin Clausen.
Ah, and you.
Yeah.
Okay. And so these Galois extensions don't have to be abelian now. You have non-abelian extensions of the telescopic sphere.
Yeah, that's right.
Okay.
That's right.
Okay.
Yeah.
And what are the GNs and the original construction in Morava K theory? Can you say what those GIs are?
You can actually just choose any open, like you can choose any exhaustive filtration on by open subgroups of the Morava stabilizer group.
Mm-hmm.
So for example, if I replace this with the non-extended Morava stabilizer group, you can choose the congruence filtration.
Yeah.
Um,
Yeah.
and you can do the congruence filtration, and essentially you can think of these Galois extensions as roughly corresponding to the TNs, like
Uh-huh.
your TN spectra. So this is kind of like the filtration of TNs that filter BP. Um,
Now, do I understand it correctly that if you have a finite cyclotomic extension of either SKN or STN, you can identify that as a localization of an appropriate um, Eilenberg-MacLane space?
yeah, yeah. So right, the construction of the cyclotomic extensions is you take the TN local sphere, you adjoin Bn of Z mod P to the K,
Mm-hmm.
and then you invert some idempotent on it. So there's some
Yeah.
idempotent that you construct using ambidexterity
Mm-hmm.
um, uh, that you invert to get the cyclotomic extension.
Right. Right.
Yeah, that's right.
Okay. Is there any, but you don't have a similar description in this non-abelian case, is that right?
No, I mean the theorem really is just that KN localization detects Galois extensions. So it's even more general than this. It's essentially telling you that any TN local ring, if you can localize it, will have the same Galois extensions, the same finite
Okay.
Galois extensions. Um,
Cool. All right.
but um, yeah, so there's no literal construction of this like that, but maybe the proof that the colimit is Rava E theories goes through comparing this tower with like comparing this with the TNs essentially.
Okay.
Yeah. And yeah. So I mean, there's no explicit comparing this for the congruence subgroup filtration with the TNs.
Wait, by TN you mean the telescope, or do you mean?
No, no, no. By TN I mean the summand of XN, XP to the
Okay.
yeah,
All
right.
right. Yeah. Yeah. We need a different symbol for that.
Yeah, 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 yeah. There should be a different notation.
Okay. Very interesting.
Mhm.
Thank you, Doug. Any other questions, anybody? So looking at this last theorem again, Ishan, I was wondering if there could be a more general categorical formulation of it, because when we look at the what we call, say, I don't know, there is this phrase called the tensor telescope conjecture for big tensor triangulate categories, which is about every definable tensor ideal being compactly generated, and there are some very neat characterizations of when, for example, that category of like DQCX for any QCQS scheme
Mhm.
satisfies that tensor telescope conjecture. So the thing that you're saying here about this infinite Galois descent, um, very neatly capturing how the TN local and the KN local versions differ. Can this be crystallized more abstractly in, like, I don't know, categorical language?
Uh-huh, uh-huh. So I don't actually know if I mean I would be surprised to be honest if okay. I want to claim it's false that this mechanism for the failure of the telescope conjecture about failure of infinite Galois extensions, I kind of want to say that this doesn't happen in ordinary algebra. In the sense that like it might be true that for some non-Noetherian rings or maybe the telescope conjecture fails, but the reason there is different than here.
Hmm.
Um, but maybe okay, another thing I can say is that like we don't so there's sort of there's the Balmer spectrum of spectra, which we understand, but there's also like the smashing spectrum. I don't know what to call it, of a spectra which classifies strongly continuous localizations. And that, so for the, if you, I think there's a map maybe this way, and the pre-image of the point that's corresponding to height n here is sort of measuring the failure of the telescope conjecture as some topological space. And we don't really understand that at all, I would say, other than the fact that it's not just a single point for n at least two.
Right. Yeah. And also, in relation to your work with Greg Arone there, you said that for the unstable version, you had to work with these good Willie towers and the interactions with the telescopes. Could you say a bit more about like how the unstable
Yeah.
version is approached?
So the point is there's a spectrum. So the key reason you can go from stable to unstable is that there's a spectrum that controls the VN periodic unstable homotopy groups of space. And that's called, it's the spectrum which is coming from something called the Bausfield-Kuhn functor. So if you have a space, there's this functor called the Bausfield-Kuhn functor, and this controls so for example, it's a functor, it's a spectrum, it's a Tn local spectrum that has the property that for example, when you tensor it with the dual of a type n complex, that's the same as taking the mapping space from a space that's representing that type n complex into X, and then sort of inverting the Vn self-map on the source of this space. So in other words, this is some spectrum that's capturing the Vn periodic homotopy groups of X. And the point is that in the case of spheres, you can show using the work of Arone and Mahold that this is a dualizable Tn local spectrum. And then there are some extra tricks that you can use involving the stable range and to show that whatever bound that you would get stably on the Vn periodic stable homotopy groups of spheres will then also give you lower bounds unstably. That's essentially the
Also,
idea.
one small comment I wanted to make regarding when I thought about this just then and I checked it now. So regarding that map from this matching spectrum to the Balmer spectrum, I think it's to
Yeah.
the Hopgood dual of the Balmer spectrum, isn't it?
Sorry?
The canonical map is from the smashing spectrum to the, isn't it to the Hofstad dual of the Balmer spectrum or to the,
You could be right. Yeah.
yeah, because I remember there was a paper by Greg Stevenson and Scott Walchin where they showed, like in general, tensor triangular language, that if a
Mhm.
certain spatiality condition was satisfied by the frame of smashing ideals, then that map was a homeomorphism if and only if the tensor telescope conjecture was satisfied by that.
Yeah. Yeah.
Yeah.
Yeah, that sounds right. Thanks.
Sorry. Yeah. Any other questions? Anybody?
That was a terrific talk. Thank you very much.
Thanks,
Yes,
Doug.
definitely. And can I also ask, so which of these papers are not out yet again, sorry? Is that some of
Right.
them?
Actually, the only thing that's out really is the failure of the telescope conjecture. Sorry about that. I'll do my best to try to hopefully not make this take forever.
Okay.
Maybe I can ask. So we know that the homotopy of the Tn local sphere and Kn local sphere are different. So, but if you look at these let's say R2 tilde and R2, I mean, or Rn tilde.
Yeah.
So is there some way to say? Okay, so I mean, if you pass to the homotopy fixed points for the Galois group, you're just back to the sphere case. But if you sort of ask about the underlying, I mean, the map from Rn or R2 tilde to R2 here, is there any chance that,
Are you asking like what
is there some sort of simpler, is there any way that some of the difference between the categories becomes simpler as you go up in the tower?
I think it'll become a bit simpler in the sense that it will get rid of the kind of finite junk that would show up because of finite subgroups of the Morava stabilizer group. So for example, like when you want to understand the telescope of a type n complex, you're going to see something in general much more complicated than what you'd see when you're studying like the telescopic homotopy groups of Yn, of these Yns. And so it's that kind of simplification that will happen. It's the difference between the actual Moore spectrum and something like Yn.
Yeah.
And so it's like replacing the Morava stabilizer group with maybe what do you call it? Like a uniform
subgroup, or
like maybe a uniform a uniform pro-p group or something. Pro-p subgroup.
Right. Yeah. No, thanks.
Yeah.
Thanks a lot.
Thank you again. John? Any questions, anybody? Well, if we don't have any more questions for Ishan, let's thank Ishan once again.
Thanks so much. Yeah.
Thank you. We are off for the next 2 weeks, and we have a talk by Kiran. I keep forgetting how to say his last name. Kiran Luchke. Is that? Oh, it's that. On the 18th of June. See you then. Bye-bye.